Hey everyone, in this mini lecture we're going to be looking at a problem dealing with power and efficiency. So here's our first example. Given a 2,000 kilogram sports car increases its speed uniformly from rest to 25 meters per second in 30 seconds. The engine efficiency is 0.8. The maximum power supplied by the engine is what we're asked to find. So we go ahead and plan it out. So what we're going to do is draw the free body diagram and also draw the kinetic diagram. After that, we're going to apply the equation of motion and also the kinematic equations. All right, so we're going to do that to find the force. All right, third, we'll determine the output power. Our output power that is required. And then fourth, we'll use the engine's efficiency to determine the input power. So we're going to use the engine's efficiency to determine the input power. Okay, so in solving, we're going to take a look at our free body diagram and kinetic diagram. So we've drawn the free body diagram and the kinetic diagram of the car as a particle, as shown. All right, so the normal force, N sub C, and the frictional force, F sub C, these represent the resultant forces of all four wheels. The frictional force between the wheels and the road pushes the car forward. All right, so now we'll look at the equation of motion. All right, so being that right will be to the right is positive, the sum of the forces, sum of F sub x is equal to MA sub x. Okay, for us that yields a negative 2,000, and then it's times the sine of 5.711 degrees plus F sub C, and then this gets us 2,000 A sub x. All right, so we're going to determine that A sub x using constant acceleration equation, right? Using the constant acceleration equation. All right, so this will yield us V is equal to V sub O plus A sub x t. And then solving, we get A sub x is equal to 25 minus 0 divided by 30, which is 8.333 meters per second squared. All right, and now what are we going to do? We're going to substitute A sub x into the equation of motion. And we're going to substitute it into the equation of motion so that we can determine the frictional force F sub C. All right, so F sub C is equal to 2,000 A sub x plus 2,000 times the sine 5.711 degrees. All right, and then we have 2,000 times 8.333 plus 2,000 times 9.81 times the sine of 5.711, and that is equal to 3,619 newtons. All right, Now we'll go to the maximum power output. All right, so this is calculated by multiplying the driving frictional force and the car's final speed. All right, by multiplying the driving frictional force and the car's final speed. So we'll say P sub out max is equal to F sub C times V sub max. All right, so this is going to be 3619 times 25, and then that gets us 90.47 kilowatts. All right, next is the average power output. Okay, so the average power output is the force times the car's average speed. The force times the car's average speed. So P out max. All right, this is equal to F sub C times V average. Okay, so here what do we get? We get 3619 times 25 over 2, and that leads us to 45.28 kilowatts. All right, and now the power supplied by the engine. So the power supplied by the engine. All right, this is obtained using the efficiency equation. So we have power Pn sub max equals P out max, and that is divided by the engine efficiency. So we get 90.47 divided by 0.8, and then it's 113 kilowatts. All right, and now we're going to do Pn. Right, and then this is equal to P out average divided by the engine efficiency again. So we have 45.28 divided by 0.8, and that gets us 56.5 kilowatts.